Thank you for the opportunity to have a little talk here. My name is Mathis Kruse from Hanover in Germany. This is me at the Country Music Hall of Fame in Nashville, so it was a great conference. I'm talking about multi-view anomaly detection from static to probabilistic modeling. So I'll be talking a little bit about the paper I presented last year at the CVPR anomaly detection workshop, and also the paper I presented this year, maybe give a little bit of an overview over the field. So anomaly detection is an interesting field. We usually train semi-supervised because we want to detect anomalies in objects. And anything that kind of deviates from the norm, anything that's unusual can usually be classified as an anomaly. So it's not that tight of a definition. So we usually only train with normal data without anomalies, and then test on both normal and abnormal data. And we can see some abnormal data on the right. And the most common data sets have very tight constraints on camera and object pose. Like you can see here, the object is always aligned in the exact same way. And that may not always mimic the way it's set up in a factory. So maybe the objects are just going over some kind of conveyor belt and they aren't really properly aligned. So at the end of 2023, a new dataset came along, MAD, MAD dataset, which had these Lego toy figurines from different poses. And during training, you had all these differently posed images with poses available. And then the task became a little bit harder because the objects were just arbitrarily placed in front of the camera. And it's much more harder to reason about any anomalies in the object because we want to talk about the object as a whole. So what do some of the anomalies in that data set look like? Like I said, during training, we have different pose information. During testing, we don't necessarily do. And yeah, the products are arbitrarily placed before the camera. And here we have a little swan, and some of the defects are missing bricks, as we can see here. And depending on the pose, that the brick is missing is easier or harder to spot. Other anomalies are also things like discoloration or excess material, but really anything that kind of damages the object can be considered an anomaly. And if it's currently visible within the current pose, then we also want to be able to detect the anomaly. So if it's not visible, then we cannot possibly find it. So that brought me to the paper from last year, SplatPose and Detect. I did together with Marco Rudolph, who's a relatively big name in anomaly detection, and my supervisor is Bodo Rosenhahn. We're here with this example of a pig, which is missing eyes from different viewpoints. And what I essentially did was leverage these multi-view training images, which are, of course, anomaly-free, so no anomalies in the data set, in the training set. And I learn a splatting-based representation of this object. And I use this to pretty much align and get reference images of these query images, and I'm thereby able to detect the anomaly, in this case, the missing eye, in all the different poses. And this is from last year's CVPR workshops. So how do we learn this? Well, I call it Pose-Invariant notion of normality. I used 3D Gaussian Splatting for it, which is also a relatively recent method, and the field has kind of been exploding on it. So many people are going into Gaussian Splatting. And as input, here we take multi-view images of an object or a scene. And yeah, we need also the poses of the camera where they are located in the three-dimensional scene or related with respect to the object. And then we, it's very simplified. We learn a kind of point cloud representation of object or of the scene, where essentially each of these points is a three-dimensional Gaussian blob in a sense that can be rotated around, and it can move around in 3D space. It has a color value and an opacity value assigned to it. And with this learned point cloud representation, we can do novel view synthesis. So we can render views from our object or our scene from any camera perspective that we want. So any possible object pose is now renderable for us if we have enough training data. And also, like I said, we only train on normal data. So in this case, this novel view synthesis also only plots normal variants of the object. So what did SplatPose do? On the right-hand side, we have an example of a test image with a discoloration down here at this little spot. And on the left side, we have a rough estimation of the pose taken from our training data set. And now we can render images of our scene, and it's done in a differentiable manner. So we can calculate a loss. And we calculate the loss between these two images and essentially apply a transformation to the point cloud, so a rigid body motion to the point cloud to have the object move through 3D space. So this is done iteratively, and with each iteration, the pose between our current rendered object and the test image get closer and closer until they are sufficiently close that we can actually pretty much just compare the two images, like pixel-wise, or we can extract features and compare these features, and thereby get an anomaly map, which shows us that actually this is the only spot where these pictures significantly deviate, and this is where the anomaly is set. So to go over the procedure one more time, during training, we have a lot of multi-view images of an object, so we train one model per object, and we learn this 3D Gaussian splatting model. Then we have a test image. In this case, a big brick is missing for this mallard duck. We roughly estimate a first initial pose, as you saw. This is done relatively simple with just extracting deep features and searching for a nearest neighbor in the training set. Then we can differentiably render our object, and we can also apply transformations, which we sample. And these transformations are applied to the Gaussian splatting model to move it in 3D space with a rigid body motion. The result can be compared to the query image with, we can calculate a loss, which backpropagates to the transformation sampler. So the transformations can be fine-tuned to the current scene. And in the end, when it's sufficiently good, we extract features and compare them to each other with a pre-trained model, a simple one, and we get the resulting anomaly map with the anomaly marked relatively well. Yes. All right, so we evaluated it quantitatively on this MAD dataset, as I talked about. And at the time, we were able to get a pretty good 3% boost in the detection OROC metric, and which was a good state-of-the-art improvement. Also, it should be noted that compared to OmniPose AD, and SplatPose are the only ones that really properly worked well on this type of data set. So all other methods, which usually just work with 2D images and are not able to include any of the pose information, they usually lag very far behind the 3D pose-informed ones. We hypothesized that this is due to the precise pose estimation of our approach and due to the high quality rendering we achieve, that we are able to outperform Omni AD. And also OmniPose AD is working with vanilla neural radiance fields, so NeRFs. And these are, of course, very slow to train in their vanilla version. And also the inference is relatively slow. So our method is just by virtue of using Gaussian splatting, orders of magnitude faster in both training and inference than OmniPose AD, which is another good advantage when you want to detect anomalies in industrial settings where you want to be very fast, usually real time. So we also evaluated the pose estimation itself. So on the right-hand side, you see a few examples of the first coarse estimate of a pose, then the fine-tuned pose by our differentiable process, and the ground truth to which we want to get, and they match pretty well on different data sets. We run this for 175 iteration steps, but we can have it run for more steps if you want to get even closer. We also evaluated this pose estimation quantitatively competing with the iNerve method, which is the basis of OmniPose AD. And the coarse pose is, of course, from where we start, and then SplatPose is able to beat out the iNerve, so the inverted nerve it's called, in both translational and rotational error on all the datasets that we used by quite a good margin. So our hypothesis that the pose estimation actually had to do with our better performance may hold true here. Lastly, a few more qualitative results and also an ablation study at that, where we reduced the number of training samples, which generally causes nerve to struggle more than Gaussian splatting. So it resulted in our method having the upper hand when using only 20% of the training data. It's still able to detect the anomaly, in this case for this turtle. And this also held for several other of the objects in the dataset. So also this pig here, where the nerve is not even able to properly align it at all. And it's the same for this penguin, where only SplatPose was able to come out on top, essentially. So yeah, where did pose-agnostic anomaly detection evolve from here, where we have multiple poses of objects? So maybe a kind of an overview of the landscape of research. New datasets came out. So last year, the RAD dataset was a direct follow-up with an dataset captured by a robotic arm swerving around objects, essentially. The M2AD dataset is from this year, and it's relatively large, and it's also very complex as it features multi-view, as we can see down here, multiple different kinds of object instances per object class, and also multi-illumination scenarios, so different type of lighting conditions, which make the task even harder. Also, a few new methods have evolved. PIAD is from this year's main track, which can be seen kind of as a direct follow-up to SplatPose in a sense, and it also played around with different lighting conditions, just like the M2AD dataset. And lastly, another main track paper, which directly built upon SplatPose, was not concerned with anomaly detection, but with scene change detection. So a scene of, like, for example, a room is captured, and then we want to see if anything at a later time has changed in that scene, which is also possible with a SplatPose-like approach. So maybe we zoom a little bit into PIAD, and we can see that they also up here trained a 3D Gaussian splatting based model. They also had some type of relatively simple best matching, so nearest neighbor matching, post initialization and optimization. And also they are matching at the end. So it's pretty much almost the same, but a few tweaks with also taking reflectance maps as a basis for another 3D Gaussian splatting based model, which takes care of the multi-illumination problem, which is naturally harder for SplatPose. So why is this title kind of wanting to shift to more probabilistic modeling? As we can see here, the 3D Gaussian splatting based models which are used are static. So they are learned once, and then anything which deviates from this model is considered an anomaly. And new datasets came out. So this is last year's main track, the real IAD dataset. And it features thousands of multi-view objects, and each object had 5 different views per instance. So they essentially were put into this machinery, and images were taken from all 4 sides and run from the top. And these are some example classes with an audio jack and a phone battery with the anomaly marked here in red. So we have, again, different viewpoints of an object, but many more objects. And these are more examples. Now the anomaly is marked in yellow because they can sometimes be hard to spot. So this is a switch, and this is a USB adapter. So for all these that I've shown, like the audio jack, the battery, we could probably think something like SplatPose or PIAD could work. because they are also these manufactured objects. They are out of metal, out of plastic, stuff like that. But it gets more interesting when we look at the other classes, like this wooden block. And we also want to detect anomalies here, like dents into the block or pieces carved out of it, scratches. And here it becomes much more difficult because, as I talked about it, this Gaussian splatting model is kind of a gold standard model, as I call it, because anything that deviates from it is considered an anomaly. And with this wood block, the wood texture is different for each wooden block because wood is just a natural resource. It has so much variance. So a gold standard is not possible. We can't learn one type of wooden texture and just have it the same for all of the objects. So this is why I came up with the paper at this year's conference, MultiFlow, which takes these multi-view images of these objects as an input, and a multi-view enriched normalizing flow essentially uses these to predict the anomaly maps, and it's able to usually find all the anomalies in all the views at a pretty good rate. And single view methods, again, which are not explicitly leveraging these multi-view connections, may sometimes fail at this task. So what did I do? I went back to normalizing flows because normalizing flows have a great tradition with our institute. And they are a type of, in the way I use them, invertible neural networks. So you can use them both ways, essentially. And you can use them for exact density estimation. So estimate the likelihoods within some feature space. So the most common example is this example of two moons of two-dimensional points in this moon shape. And the normalizing flow is able to map each of these points into this space on the right, which is distributed as a standard normal Gaussian. And essentially, we could also go back because it's invertible, but in this case, we're only interested in this direction where we map it onto a Gaussian. And what's done now is that the points that get very close to the center of this Gaussian space, essentially, are the ones with the high likelihood. And the points that are farther outside are the ones with the lower likelihood, as we can easily calculate. And by training our normalizing flow only on the normal data, as we always do in anomaly detection, we pretty much ensure that the high likelihood regions are all covered with normal samples, and the low likelihood regions are essentially forced to contain the abnormal samples, just by virtue also of being invertible. So for this, we need a special type of architecture, which are called invertible coupling blocks. You can ignore this conditioning for now. What essentially happens here is that an input comes in, it gets permuted channel-wise, it gets split across the channel dimension. So this upper part is fed into neural networks S and T to predict a scale and a translation vector, which is multiplied and added to the other part of the input. And this also gets fed into another S and T network to also scale and translate the other part, and then it gets concatenated again. So why is this invertible? Well, we could also go from the other side, come from here, split it up, first go down, and here calculate the same S and T values as before, and essentially subtract them and divide them. And this works in the other direction as well, and we have ensured that it's invertible, even though these S and T networks are neural networks in this case and can be as complex, as non-invertible as we want them to have, or as we want them to be, rather. So yeah, I took a little bit of inspiration from my colleagues' work with CS flow, which already used normalizing flows for anomaly detection in a multi-scale fashion, where the image is resized to different scales. So what did I do for MultiFlow? First, I boosted the performance with a foreground extraction. So the models for extracting the foreground or extracting essentially dichotomous image segmentation are getting very good. And they just out of the box work really well on all the anomaly detection datasets. So we only focus on the object and not on the background, which may confuse the model. I then want to, at each step, essentially aggregate information across neighbors. So this yi is essentially one view of my object. And I want to process it to some f cross, which is just some kind of ResNet block, or in my case, convolutional blocks. And then I'm add onto it a weighted sum across all the neighbors of this view, which are also processed through their own convolutional blocks. So essentially, each view has a feature vector, which is pre-analyzed with a convolutional block. And then this one connection is just for this view by itself. And then there is another weighted sum across the other connections within the views. And as the dataset is currently laid out, I added views from neighbors to neighbors. So these are the views on the side of the object. And I added connections from the top view to all the down views, because what the top view sees, usually all the views from the side are also able to see. And then all these views get processed again in another one of these blocks, and they are chained together, essentially. The results are pretty good, especially in the detection metrics, where sample-wise detection is now detection of one instance of an object. So 5 images make up one instance, make up one sample here. But we also evaluate image-wise detection, which takes each image, even the ones from the same object, as different from each other. And we are able to outperform the state of the art by a pretty good margin. Sadly, the detection metrics are also not bad, but they aren't as competitive as our detection metrics, which is a common problem for normalizing flow methods, and maybe also a problem for my future research. So we also run an ablation on the type of fusion, essentially, I detailed on the last page, so where we connected neighboring views to each other. And we find out that the way we have designed it is especially a great boost for the sample-wise prediction, because here information from one view can flow to another. So an anomaly that is hard to see in one view, but is still present, and it's easy to see in another. That's where the information can flow, and that's where method shines best. It's not as great an improvement for the image-wise detection, but still somewhat small improvement. There are also lots of quantitative examples in the paper. You can look at them. Usually you have to scroll in pretty far, because as in anomaly detection, the anomalies are very small usually, but the performance is still very satisfactory in this case. So another very small overview on where to go next from here. With this year's CVPR, even more complex datasets have came out. So the Manta dataset is a very interesting one, which also has multi-view images of sometimes even harder things like these agricultural products. So that's an interesting one to look out. And they also have interesting text description of the anomalies. So anyone that's working with language models and vision models, maybe look at this one. It's an interesting combination from the two. And also one field which I find very interesting is the more 3D geometry informed methods, which directly encode the geometry of the scene into the process of gathering the features. And that's also very interesting in my opinion, but it's an archive preprint, very new. Lastly, at TNT, which is my institute here, and Hanover, we have by now a small history of anomaly detection models. So we have quite a few RGB methods like the Differentiable in 2021 and the CS flow that I already mentioned. We have methods that work on RGB images and also depth data to detect anomalies. We have, of course, the multi-view methods, which I've just presented in this talk. And we also have a data set and also a method for detecting anomalies in time series. So it's a robot picking up things, and we track time series of some of the signals. It's also an interesting data set, and you can use this QR code to get to our website and get your hands on all the code, because for all methods, all the code is always available. Yeah, lastly, thanks for all your attention. You can also scan this for my papers, so the multi-view stuff and also the code, because as I said, it's all available, and I'm happy to take any questions.
Fantastic. So I did include a link to the GitHub project page in the chat, should be the last message there in the chat. Let's take a couple of questions. The first one is, what software did you use to generate these splats?
So that's actually just the vanilla 3D Gaussian splatting implementation as it's on GitHub, because I made this work when Gaussian splatting was so very new. So it was just the original from the original authors, so Kerbal et al., just the GitHub repository. And also, if you clone SplatPose, then it's also gonna grab all that code, and it's that's what it's based on.
And then continuing on the splats train, do you eliminate spherical harmonic data from the splats?
Interesting, yeah. Actually, we observed that sometimes the reflection effects can kind of get bad when we rotate it around a lot. So we limited the spherical harmonics to degree 0, which means that they pretty much just have one color from every direction. And this just makes sure that the object does not change color when viewed from another angle. But for more complex objects, which also have more complex materials in them, taking higher spherical harmonics would probably be good to also model them.